Hello, my name is Anuj Bhatia, and this is my Physics 2211 Lab 5 Choose Your Own Adventure. So, the purpose of my lab was to simulate and prove how momentum is conserved between objects in an ideal situation using GlowScript, and I simulated objects of various masses, velocities, and angles, and displayed how momentum is conserved after a collision. And some physics principles I used in this lab were kinetic energy, conservation of momentum, and the momentum principle, and my results showed that momentum is conserved in collisions regardless of object masses, velocities, and angles in systems where no outside forces are acting on it. Some of the main physics ideas and principles I used were kinetic energy is equal to 1 half mv squared, momentum is equal to mv, the position update formula, the conservation of momentum, and then finally the momentum update formula. So some initial conditions are the system consists of the two masses, surroundings is nothing because it's an ideal system. The masses change depending on the simulation that I've decided to run, which we'll see later, and same thing with the velocities and angles and positions, and the initial time was 0 seconds, and the change in time was 0.001 seconds. So, some details about the computational model in GlowScript. This first chunk of code sets the simulation scene, masses, and radiuses of the balls, and the initial angles and speeds, which again will all be changed depending on the scenario that we're analyzing. And then the variable e, which sets the collision as perfectly elastic because it's at 1.0, and delta t. So this next part of the code just creates a function to convert degrees to radians, which will be useful for our angle analysis if we launch a ball at a certain angle. And then we turn the velocities into x and y components if there are angles, if there is an angle, and then it creates the balls and sets initial positions, creates the momentum variable using the formula mass times velocity, and it creates arrows to display each ball's velocity and total momentum. And lastly, it creates labels to display momentum, total momentum, and energy and collision information on the graphs after we run the code. So this next chunk just creates graphs for the momentum, each mass, total momentum, and kinetic energy, and creates a function to calculate the magnitude of the velocity. And this part of the code sets normal and tangential motion vectors, creates normal and tangential velocity components, and calculates new velocity using conservation of momentum and updates the momentum. And using a while loop, it runs the simulation for 3 seconds and updates the ball position and calculates the distance between balls. So then if the distance is less than a diameter, then a collision happens, and it then calculates how the new angles of the balls that they'll move at and prints that a collision occurred. And it makes sure that the balls bounce off instead of overlapping or going through each other if a collision happens, and then it updates the ball position and arrow position size and total momentum depending on the collision. So finally, it updates all the labels in kinetic energy and updates each graph at the end, and then it iterates to the next time step. So this is the first analysis that I decided to analyze, and it's a glancing collision, and you can see the initial conditions on the left. And a glancing collision is just that when two balls hit each other and then they both go off at certain angles, so it's not head on. So analyzing those results, the initial momentum of ball 1 is 4, 0, using mv. Initial momentum of ball 2 was 0, 0, 0, and the total momentum was therefore 4, 0, 0. And from the video, we can see the final momentum and final momentum of ball 1 and 2. And adding those together, we again get 4, 0, 0, which means that final momentum is equal to initial momentum and the momentum is conserved. And you can see on the graphs on the right that momentum in the x and y directions and kinetic energy are flat. They're just flat lines, and therefore they're both conserved. So this next analysis is on the head-on collision. So again, initial momentum of the ball 1 and 2 and total initial momentum is the same as the glancing, but the final momentums change, and you can see those in the video. And again, if you add them both, then the vector results in 4, 0, 0, which is the same. So final momentum again equals initial momentum, and momentum is conserved. And again, you can see on the graphs that total momentum in the x direction, because there's no y motion, and in this simulation, and kinetic energy don't change again, and they're both flat. So some discussions are the results that we saw. So as the computational model shows, in an ideal scenario where no outside forces are acting on the system, momentum and energy are always conserved. And as it can be seen, regardless of mass, initial velocity, angles, and the initial momentum was always the same as the final momentum. And we could do numerous other simulations messing with angles, masses, and velocities, but the end the result would always be the same. So some possible sources of error are, in reality, there would definitely be other forces acting on the system, such as friction and air resistance, and that means some momentum and energy would be lost to things like heat and sound, so it wouldn't be fully conserved as the model shows. And in addition, the model doesn't account for possible rotation or deformation of the objects from the collision, all of which can affect momentum being ideally conserved. So an additional question is, why does the kinetic energy graph stay flat for fully elastic energy, and how realistic is this? So because the collision is perfectly elastic, no kinetic energy is lost or gained and before, during, or after the collision, which means that there is no friction or air resistance, no energy was lost to heat or sound, and the masses were deformed during the collision. So therefore, final kinetic energy is equal to initial kinetic energy, and the graph stays flat. And in reality, this is not very realistic because there's almost always other forces acting on a system. So it's hard to find or actually make an ideal system. So additional question 2 is, what does it mean when the two angles of the masses add up to 90 after the collision? And so the only way for this to happen is if the two masses are equal in mass and the collision is perfectly elastic and the initial velocity of the second mass is 0. This is because the momentum and energy from the first mass must be split equally after the collision, and this can only happen if the two masses are perpendicular after the collision. Angles that don't add up to 90 would result in some energy being lost in a perfectly elastic collision, which is not possible. So that's my lab, and thank you.